So this is, we're doing a couple of sections in chapter 1. This is a little bit of review. It's one of the few things that they left in from the old standards that is actually review material. So we're in section 1.7, and we're going to talk today and on block day about combinations of functions. Before we start combining functions, let's just remember quickly what we mean, what are we talking about when we're talking about a function. What makes, we have some kind of relationship between x and y. What is it that makes it a function? Why do we call something a function versus just an equation or something else? What's special about functions? Anybody remember? Let's see, what if we graph something that is a function? How do we tell from looking at the graph if something is a function? The x's don't, what did you say? They don't compete? If they don't repeat. So the x's don't repeat. So there was, so you're, I think what you're saying is what I'm looking for. There's a test. Thank you. There's a test that we can use when we have a graph to tell if something's a function. Anybody remember what that test is? The vertical line test. So one thing that's special about a function is if we graph it, it passes the vertical line test. And I think what Jack was getting at is the x's don't repeat. The other way, if we're looking at a table of values, if we're looking at the numbers that go into the function, for every x, there's exactly one y. For every input, there's exactly one output. So if we have our classic picture of a function is like a parabola. For every x, there's exactly one y. If there were two y's for one x, we would have something that looked like, possibly, like this. So for this x, there are two y's, and this is not a function. So it doesn't pass the vertical line test. And for this for each x on this one, there are two y's. So that's how we tell if something's a function. It passes the graph. If we look at the graph, it passes the vertical line test. For each x, there's exactly one y. So I think that's what you were getting at, Jack. So what makes functions important? The reason that we're working with functions is functions have nice properties, and we're going to talk about some of those properties as we go on. And the nice properties of functions let us work with them, let us make some generalizations about functions that make them easier to work with. So that's why functions particularly are interesting. When you go on to calculus, functions, when we have a function, we a lot of times we're interested in functions that have particular properties that make them nice and easy to work with. What we're going to talk about today is how we combine functions. So the first thing that we're going to do is just talk about combining them by arithmetic. Or I'm going to say not by, instead of by, I'm going to say with. So our notation, if we have functions, we have two functions f and g. Just so we're clear on our notation, the way that this book likes to notate these things. F plus g the way our book writes them, f plus g, we're just adding the two functions, f of x plus g of x, just like we'd expect. We're just adding the two functions together. Same thing for subtraction, f minus g. We just subtract the two functions. F times g and the way we write that is f times g with the x in the parentheses. We're just multiplying the two functions. And then our quotient, dividing f over g. We're just dividing the two functions. And what do we have to be careful with when we're dividing? For this last one. What do we have to be, what has to be true of g of x here when we're dividing these functions? What gives us a problem if we divide by it? 0. G of x can't equal 0. We don't want to divide by 0. So when we're dividing functions, if a lot of times the problems in our homework will ask us to add these functions and find their domain. When we're dividing functions, our domain restriction is part of our domain restriction could be where the denominator is 0, where g of x is 0. We don't want to divide by 0. That gives us a problem. So let's look at a quick example of combining functions with arithmetic. This is I'm going to go through this pretty quickly. We should all, I think we're all pretty good at this. I just want to make sure we get a little refresher here. So so here for our example, I'm going to say that f of x is x squared plus 2x, and g of x is 2x plus 1. So f plus g I'm just adding these two functions. It's just going to be x squared plus 2x plus 2x plus 1. Combine like terms, so I just get x squared plus 4x plus 1. Just add those two functions together. F minus g, same thing, subtracting x squared plus 2x minus, and when we subtract a function, it's important to remember, I always like to put this second function in parentheses, so I remember to distribute that negative sign. So I have to remember that my negative sign gets distributed here. So I get x squared, 2x minus 2x is 0, and I get a minus 1. X squared minus 1. F times g. I'm going to multiply these two functions, x squared plus 2x times 2x plus 1. And to multiply this, I have to FOIL when I multiply these two parentheses. So when I FOIL this out, I get, the first is 2x to the third plus the outside, x squared. The inside is 4x squared plus the last is 2x. Then I'm going to combine my like terms, 2x to the third plus 5x squared plus 2x. And finally, f over g of x. We're just dividing these two functions. And what do we have to be careful with here when we do f divided by g? What x value are we excluding from our domain? The denominator can't be 0, so 2x plus 1 is not equal to 0. So x not equal to what? There we go, negative 1/2. To solve this for x, and we're leaving that out of our domain. So x doesn't equal negative 1/2, because that would make the denominator 0. Everybody good with this? And later on in the course, we're going to learn how to do a little more, and I think you guys know a little bit already, how to do a little more with this kind of division, to simplify this a little bit. So I'm just going to put a little mark here. Always remember when you're dividing to think about how you might need to restrict the domain. You don't want the denominator to be 0. So questions about combining with arithmetic. You're just doing the operation that whatever this is telling you to do. All right, here's where it gets a little trickier. Again, we're reviewing some, so this is shouldn't be totally brand new. Compositions. Compositions of functions. Compositions are when we take one function and plug that whole function in for x. That's what we do when we're doing compositions of functions. So let me give you a definition first. So the composition, we have our functions f and g. We write f of g with a little circle of x is f of g of x. So what this tells us is we're plugging in the entire function g for x. That's what the composition tells us to do. We plug in the entire function g for each x that we see. And when we have to be careful with the domain of a composition. So the domain of our composition is the domain of G that are also in the domain of F. And basically what that's telling us is we have to look at the composition. We have to leave out anything that's not in the domain of G, and then we also have to look at the composition to figure out the domain of the composition. And the way I think about compositions is I think about the inside function. So g of x is the inside. I think of g of x as the inside, and f as the outside function. So for our domain, we have to look at the domain of the inside function and figure out the domain of the final composition, the whole big function. We have to look at the inside function and the whole composition. So we will we'll do some compositions and we'll look at the domain. But domains or compositions are something that that everybody I think has worked with a little bit before. So let's do a couple of examples and we'll figure out, we'll look at some where we have to worry about the domain. Any questions before we go on? Okay. So an example. So we have f, we'll use our same f's and g's. F of x is x squared plus 2x. And g of x is 2x plus 1. We'll do f of g. So what this tells us is we're going to plug in g into f for every x we see. So wherever I see an x in f, I'm going to plug in g. So I get 2x plus 1 squared plus 2 times 2x plus 1. And in order to square this, I'm going to FOIL. When I FOIL this, I get, I'll rewrite this really quick so we know what we're talking about. So this is 2x plus 1 to remind us that we need to FOIL. And here I'm going to distribute. When I FOIL this, I get 4x squared from the first. The outside is 2x and the inside is 2x. So when I add those together, I get 4x. And the last is plus 1. And then I need to add this. And when I simplify, I get 4x squared plus 8x plus 3. So that's f of g of x. If I want to go the other way, g of f. This time I'm going to take f and plug it in for x everywhere I see x in g. Just going the other way. So f of g, I'm sorry, g of f is 2 times x squared plus 2x, plugging in f in here, plus 1. Now I just have to distribute. I get 2x squared plus 4x plus 1. So that was a little easier composition. On this example, do either f or g have any restrictions in their domain? No, there's no numbers that give us a problem in 2x plus 1. There are no numbers that give us a problem in 2x or 2x plus x squared. So our domain of our compositions aren't restricted in these particular functions. So let's look at one where we do have a restriction in the domain, where we have to worry about our domain of the composition. So in this example, I have f of x equals 1 over x minus 2. And g of x is the square root of x. We want to find f of g and its domain. So let's form the composition. What's going to be the composition f of g? Who can help us out here? 1 over, perfect, 1 over square root of x minus 2. So there's my composition. I just plugged in g in x, g for x everywhere I saw an x and f. So that's my composition. Now I need to figure out its domain. What's restricted from the domain of g? Negatives, right? So the domain of g of x is that the number has to be greater than or equal to 0. So we know from g that we can't plug any negative numbers into this function. Negative number is going to give us a problem in the square root. So we know that x has to be greater than or equal to 0. That comes from g. And then what about the entire composition? What number is going to give us a problem in the whole big composition?
4.
X equals 4. Because when we take the square root of 4, we get 2. And then we get a 0 in the denominator. So x cannot equal 4. So we had to restrict our domain based on what could go into g, and we had to restrict our domain based on what was going to give us a problem in the entire composition. So we looked at the domain of g, and we looked at the domain of this final function. And these domain restrictions, neither of these affect this at all except for x equals 2. The only problem we have in f of x is x equals 2. But the domain of our composition is more restricted. Are we good with that? Questions on what we did here? All right. One other example that I want to do, one last example. You'll see a few of these in the homework. And this becomes more important when you move on to calculus. But we want to figure out, if we're given some function, we want to figure out, is this function a composition of functions? Can we figure out two functions that if we make a composition gives us the function we're looking at? So let's look at an example of that. We're kind of figuring out how do we undo a composition. So here's our example. We have h of x, some function, is x squared plus 1. I don't like this one. I'm going to do a different one. H of x is 1 over square root of 3x plus 1. We want to find f of x and g of x so that f of g of x equals h of x. So we want to figure out two functions that when we make the composition, we get h of x. Anybody have an idea of how we might do this? What do you think, Kevin? So you're saying, say it again, f is 1 over x? Perfect. Does everyone see what Kevin did there? He said, okay, I have one function. My one function is 1 over something. So let's make f just 1 over x. And then g, if I plug in g for x, I want to get this thing. So we can make g equal square root of 3x plus 1. So we're kind of figuring out how we can combine two functions to get a composition. let's let's look at another one. H of x equals x plus 1 squared minus x plus 1. And we know that h of x equals f of g of x. So how can we pick out our f and g to make h of x a composition of f and g? So one person thinks they know. Anybody else think they know here? Couple. So the way I think of these is inside function and outside function. So if we look at this, function, what quantity is inside? What quantity is inside the function, inside the parentheses? X plus 1, right? So let's let g of x be x plus 1. And the outside function is what are we doing to this inside function? So let's say f of x equals x squared minus x. So I have something squared here minus something else. So my inside function is x plus 1. My outside function is x squared minus x. If I make the composition of those two, I get this original function. Questions on that? I think once you try a few of these, it'll make a little more sense. And this, we won't do a lot with this idea, but in calculus, figuring out what the inside function is, what the outside function is, does play a big role. Any questions on combining or compositions of functions? All right. Homework. We're on page 74. All right, there you go. Got a little time to work.